So we've talked a little bit about the design of an internal manifold. What I'd like to talk about now is like, okay, what are the practicalities? What are the types of dimensions from a fluid mechanics perspective that we're going to need to build into these plates to basically have this thing function properly? You have these channels, you're trying to feed fuel up through the stack. That incurs a pressure drop because you are flowing gases up through the stack. And then you're flowing gases across each cell, and that also has pressure drop. Those pressure drops are not big. They're just gases. You can flow through these gases at reasonable rates without much pressure drop. That's not really the problem. The problem has more to do with fuel distribution. So once you send fuel into a manifold or you're pulling air out of a manifold, you can't control the individual flow to every cell. So you need to design this thing with the appropriate space between the interconnect and the plate and the size of the manifold holes so that the pressure drops in this whole thing are balanced. So at the bottom, you've got a fuel inlet and you've got the exhaust outlet. The cell that's closest to that manifold feels the biggest pressure drop. So it's going to have a flow rate across it that's given by the delta P from one side to the other. Well, if you go up the stack even further to the top, that's separated from the bottom by some distance. And there's pressure drop as you go up the stack, and there's pressure drop as you come down. And so if you go to the very top, there'll be a different pressure drop. And if it's a very tall stack with long manifolds, that pressure drop difference can get really big. If the pressure drop is not the same, then the flows are not the same. You've got more fuel going on one cell and less fuel on another. And that could be bad if you think about the utilization, because the current is the same. Current is going through every cell. So I'm using up the same amount of fuel on every single cell. But if I use up the same fuel on every cell, but I'm feeding less fuel on some cells than others, it means the utilization is higher on some cells than others. So some cells might be going to 90% utilization, while other ones are down at 75 or 80% utilization. That can lead to problems in the operability of the stack, because if you start, pulling more current, all of a sudden you could exceed 100% utilization on one of the cells, and that causes a voltage reversal, which then destroys those cells. So a common way that stacks fail is through this problem of maldistribution, or the fuels not being uniformly distributed to all the cells. The example I'm going to take is returning to this sort of running example we've been working on, our 20,000 watt data center device. We were just modeling, based on natural gas. One of the conditions we were looking at, we ended up with approximately 12 by 12 centimeter cell to just sort of sketch conceptually what we're looking at. Imagine this is a externally manifolded device. It's not, but I want to think about for the moment what the fluid mechanics situation is. We've got this cell and we've got an interconnect, and the cell width, the active area, is 11 centimeters from the calculation we were doing the other day. So I'm actually just going to call it a 12 by 12 centimeter cell for approximate reasons. Imagine a square cell, 12 by 12. Looks kind of like that. And we've got this gap through which we're blowing the fuel or air. And in this case, I'm going to worry about the air, because as we've been talking about, we in the SOFC, we're using a lot of excess air to do cooling. So from a pressure drop perspective, the air is a major consideration. What I want to think about is, if we're feeding air across this cell, how much pressure drop do we get? Is it something we can sustain reasonably with a blower? And what does it mean for distribution? So on one side of the cell coming in, we're feeding in our air, and it's going out the other side. So let's think just for a moment about, like, what's the pressure drop going to be for this airflow? And for the moment, let's start just with an approximation that this is going to be 1 millimeter. The fuel flow to this cell, I think we calculated, was 4.3 times 10 to the minus 5 moles per second. And this was producing 18.6 watts. And we had a 36.9 to 1 air to fuel ratio due to the cooling requirements. Let's think first about what's the volumetric flow rate. This is a fairly high temperature. At higher temperatures, the gases expand. So you might expect the volumetric flow rates and thus the velocities to be larger. So first of all, what's the molar volume? I'm going to assume it acts as an ideal gas, and that we're at 1 atmosphere. Temperature is variable, but I'm going to use sort of an average temperature, which is around 1,000 Kelvin. That works out to 82,000 centimeters cubed per mole. So quite a bit larger volume than we have at room temperature. The volumetric flow rate, this would be our fuel flow times our ratio. That's to get the air that we're flowing times the volume. That gives us centimeters cubed per second, which is about 130. So think about the average velocity. Sorry, I'm using V in two different contexts. I've got a lowercase v for molar volume, but I'm using a lowercase v with average bars around it to indicate velocity. This would be the volume flow rate divided by the area. And by area, I mean the cross-sectional area of flow. This would be 130 cubic centimeters per second. And then the area is 12 centimeters wide by 0.1 centimeters tall, because we're using a 1 millimeter gap. So that's about 1 meter per second. Is that a big flow or a small flow? One way to think about it is in terms of Reynolds number. So the density, this would be the molecular weight divided by the molar volume. I'm going to take the average for air, it's 29 grams per mole. And then our molar volume. And this gives us 3 times 10 to the minus 4 grams per centimeter cubed. And then I looked up the viscosity, and that's for air at 1,000 Kelvin. So one thing we have to ask is, if we're going to calculate a Reynolds number, what is the characteristic length? Usually it's defined by whatever the minimum distance is. So in this case, our gap looks like this, and we're flowing, this way. So if I drew a velocity profile, this is not a good enough drawing, sorry. Let's try that again. Where this distance, I'm going to call 2b, which is what we're saying is a millimeter. 2b, because oftentimes in fluid mechanics textbooks, the distance b is from the middle to the edge. So there's symmetry. And then we're flowing over a distance L. As a result of that, we're incurring a pressure drop. So usually in sort of one-dimensional flow situations like this, we would define a Reynolds number based on that characteristic length. So we'd use B or we'd use 2B. So I'm going to define a Reynolds number as rho times 2B times the average velocity over mu. So Reynolds number is going to be about 9. You have to recalculate all that. What did you guys expect? Did you think it would be big Reynolds number or small Reynolds number?
I thought it would have been bigger.
Yeah, and that's what most people will say. A meter a second through this tiny little gap? That's turbulent flow for sure. So it's not. And this is a general thing in fuel cell engineering. It's both a good thing and a bad thing. The bad thing is that because it's not turbulent, you tend to not get very good mixing. You tend to have a harder time achieving uniformity of the gas flows. You have maximum velocity in the middle of the stream, and then it tapers off to the two boundaries. That can create mass transfer effects at much lower current densities than you would expect. It can lead to maldistribution. There's all kinds of issues with it. The good news is it's very simple, much, much simpler than if we had, turbulence, where we'd have to deal with probably a lot more empiricism and having to do a lot more measurements to make reasonable estimates of what the pressure drops are. I think this is probably one of the first problems you solve in fluid mechanics, the parabolic velocity distribution in a gap subject to delta P over distance L. Assuming it's one-dimensional and everything's translational symmetry and all that stuff, and we have this nice parabolic velocity profile, we can just look up the equation for the delta P over L it's going to be 3 times mu times the average velocity divided by b squared. So if we multiply this all out, this is going to be 5 pascals per centimeter. So over 12 centimeters, delta P is going to be about 65 pascals. An atmosphere is 100,000 pascals. So this is a very small fraction of an atmosphere. This is not a problem. We're going to be able to do this with some type of air blower, right, of the type that you have in your furnace. And maybe we might want the gap to be smaller, but with 1 millimeter, we're not going to have a problem, even with the fairly high flow rates that we're talking about here. But this could have some implications. In particular, what is the way that we're distributing this air to all these different cells? And is that something that is going to become an issue when we start thinking about the manifolds? If we draw what this thing looks like, we've got a whole bunch of cells that look like this. And to remind you, we've got manifolds. So, we're feeding air in like this. At each point, we're then flowing gas through the cells. And then we're collecting it at the other side and pumping it back down through another channel, which is running up and down through the stack. So if I start sort of thinking about the coordinate system here, I'm going to call this Z. We have a height of our stack as well as our length of the stack. This is some height H, I'll call it. And so what we're saying is we need a pressure drop of 65 pascals from the left side to the right side. And we'd like it to be uniform because we want the same flow of air across every single cell. Maybe we can tolerate some variation in airflow, but remember, airflow is tied to cooling, and cooling is tied to temperature. We've assumed we can get a certain airflow in order to maintain the temperature of the stack locally. If we have more airflow at the bottom because the pressure drop is bigger, then that could lead to maldistribution of the air and thus a non-uniform cooling in the stack. So you can think about what the pressure profile looks like. So let's try to sketch that. I'm not calculating this, I'm just kind of making a guess of what this is going to look like. So here's the coordinate C. We're going from 0 to H, where it's our total height. I'm going to call pressure over here P1. P1 is higher than P2, hopefully by 65 pascals. So here's P1, and here's P2. This is the pressure axis. And P1 is higher than P2 by delta P0. But what's going to happen as this gas is going up the channel, that's also subject to the same laws of fluid mechanics. Again, if we're talking about laminar flow, pressure drop is proportional to the flow. The flow is maximum at the bottom because we're putting in all the air at the bottom, and then it's maximum at the on the exit side, on the exhaust side too, because it's maximum downward of exhaust. And so that pressure drop per unit length, or per unit height in this case, is going to be greatest right at the bottom, and it's going to drop off kind of like that. And then meanwhile, on the other side, we might expect something like this. The reason I think it flattens out, or you might expect it to flatten out at the top, is that as you bleed off air into each cell, the flow rate in the manifold goes to 0 as you reach the top. Pressure drop per unit length goes to 0 because the flow rate is going to 0. So anyways, delta P is going to be a function of position. And so this is the problem. Delta P at the bottom of the stack is bigger than delta P at the top of the stack. And so there's going to be flow variation. I'm going to try to develop a simple model. This is a problem you may have seen in some form or another. It's basically the problem of a soaker hose in your garden. It's a section of hose that either has holes in it or it's made of vitreous rubber and kind of leaks everywhere. So you feed water into one end of it, and then the water weeps out or sprays out of it at a rate that's proportional to the pressure at that point. Pressure is highest where it's closest to the wall. You get the largest flow, and then at the very end of the soaker hose, you get like nothing. Anyway, this is exactly the same problem. You guys remember shell balances. I'm basically going to construct a shell balance. So here's the z-axis. Our height is h again. Our manifold, I'm going to picture it as a uniform cross-sectional conduit. Maybe it's circular, maybe it's some other geometry. Imagine we take a slice of that geometry of thickness dz. Into the bottom of this thing, we've got a total flow of our air. And I'm going to define the pressure here. This is P1 max. So the maximum pressure is the pressure at the bottom, and then that pressure drops as the gas flows up. So if we think about sort of just a material balance here, we can say that whatever flow of air you have at point Z, if I look at the difference between that flow minus nz plus dz, that has to be the amount of material that is going through one of the cells. So we're going to make an approximation. I'm going to make a hopeful approximation that the flow rate, n dot tote, that's flowing in the bottom, is distributed uniformly throughout this whole stack. And if that were true, then I could take n dot tote and just take it as a fraction dz divided by h. So that kind of makes it as simple as possible for us to solve, because we don't have to think about the details of the pressure drop across the cells at this point. So dn dot dz, this would be minus n dot tote divided by h, or n dot is equal to minus n dot tote times z over h plus a constant. And I have one boundary condition. I know at z equals 0, n dot equals n dot tote. So I can plug that in, and we're just going to get that C1 is n dot tote. So n dot is going to be n dot tote times 1 minus z over h. That's, I think, kind of intuitive. If we have uniform flow across every cell, then our flow rate in the manifold should just drop off linearly as we bleed that gas off, and it'll go to 0 when we reach z equals h. We can take that and then try to put that through the fluid mechanics. This is where I'm going to go back to Dean again and think about the pressure drop in a pipe. If it's circular, then we can say that dp of z, dz, is 8 mu v divided by the radius, r squared. If I take the velocity and I express it as a mass flow, we'd have m times n dot. This would end up being minus rho pi r squared for the area times r squared, which is in the denominator because it's an r to the fourth, divided by 8 mu times dp 1 dz. So putting that together, we'd have dp1 dz is minus 8 mu times the molecular weight rho pi r to the fourth times n dot tote times 1 minus z over h. And so we can solve this knowing that the pressure is maximum at the bottom. We will have this P1 is going to be P1 max, and it's going to drop off parabolically. And then you can imagine doing this on the exhaust side as well. Flow rate will be slightly less on the other side, but recall that we have this massive excess of air, and also it's mostly nitrogen, which is not being consumed. So the amount of actual volumetric flow rate that's decreasing as a result of the reaction is very tiny. So I'm just going to treat it the same way on the other side. And so we'd expect by symmetry, and so this difference, if I think about delta P from one side to the other, I mean, it's delta P will be a function of Z. What I want to think about now is how much variation are we willing to tolerate? One way to think about this, define variation in terms of the relative change of pressure, because that translates directly to the relative change of flow. I'm going to define that as delta P at the bottom minus delta P at the top divided by delta P at the bottom. So whatever delta P we have at the bottom, we don't want the change in that delta P to be a very large fraction of delta P. If it were like half of the maximum delta P, then we'd have half the flow rate at the top. which I think would be bad. So our variation is telling us, sort of on a fractional basis, how much the flow rate is going to vary from the bottom to the top. Assuming we pick a number, we say, okay, we want less than or equal to have less than or equal to a certain value, we can solve for R. Let's say, as for sake of argument, we want this to be less than or equal to 5%. We're just going to take this formula, plug it in, and calculate the variation. And it's going to be 8 mu capital M times n dot tot times h over rho pi r to the fourth times delta p at the bottom. And I want this to be less than 5%. And if I take all the numbers that I've been using, we plug our 65 pascals into delta P and so forth, and solve for R, we get a radius of 2.6 centimeters. That's about an inch. And that's the radius. So we're talking about a 2-inch diameter hole, 5 centimeters total for a cell that's 12 by 12. We're going to need port dimensions that are kind of on that order of magnitude. So this is the issue that we have to think about.